So I started recording it. Okay. So do you guys see my screen?
Yeah, we can see your screen.
Okay, good. So we discussed order one, right? You look at the order one graph, it is like single, same, everything, right? If you look at linear, that is the order n operation, it is, you have a graph like this, where this is order n, right? N square, like we said, two for loops, right? And there's some constant time of doing things. So you look at order n square, how it goes, how it becomes very steep, right? Typically, in any websites or any of these user-facing operations, they typically try to keep it at order 1 or order n or log n. As soon as it becomes n square, normally it doesn't scale, right? Log n. Now, so everybody clear with the n square? What n square is? Any questions? Okay. So can somebody explain what log n is? What is log n complexity? Hello?
Reading a value, finding a value in binary search tree.
Yeah. So essentially what it is that at each time you're trying to reduce the problem by half, right? So if there is a problem like binary search, I think a lot of people might not know binary search, but essentially you have a list of sorted. Let's say you have a list of sorted numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you are trying to find, let's say, 6, right? So the first thing you do is you try to say, okay, I'm going to hit the midpoint in this sorted array and see if that middle number is greater than me or smaller than me. So let's say it hits 5. Since 5 is greater than, smaller than 6, so you can assume that the number 6 will always be on the right side of the array. It cannot be on the left side, because 1, 2, 3, 4, which are smaller than 5, have to be on the left side. So that's how you reduce the space of searching for that number. So you don't have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but you can say, okay, from 5, I just need to now look at 6. And then next operation also, you can do the same thing. So instead of, you are at 6, you're at 5, you say, okay, I'm going to take between 5 and 10, a middle number, which might be 8, right? So you could hit it and say, oh, well, it is greater, 8 is greater than 6, so it should be on the left side of 8, not on the right side. So this way, within 2 or 3 operations, you are able to reach your number. Versus if you do an order n, then you are doing counting one first, comparing the first with the second with 6, then second number with 6, third, and then you'll do all 8, 9 operations to find where that number is, right? Any questions? So the interesting thing in log n is that as n increases, the spike or the amount of time doesn't increase at that same rate. If you look at n square, you see that as n increases, the n square, it really hits the sky, whereas this one kind of flattens out as it moves, right? So n log n is, there are a couple of algorithms like sorting algorithms that have n log n. Does anybody want to explain what n log n would be?
So any sorting algorithm. So if you are given any large set of numbers and you have to sort them, you typically, most sorting algorithms are n log n.
Yeah. So like heap sort, merge sort. Let's come to these algorithms later on. Okay, and then you can kind of get a hang of what n log n is. So this I wanted to give a little idea of what we have discussed right now. You know, what we've discussed right now, and show you that how different algorithms,
Hello, Teddy.
different complexities, how they increase.
నేను నీకు మళ్ళీ ఒక అరగంటలో చేయను మీటింగ్లో ఉన్నా.
How they typically increase with time. So why did we talk about all of this? So that I started with array and then I kind of dived deep into complexity theory, right? So now, given that we understand a little bit about complexity theory, let's say you have an array and you want to put a value 1 at the very first location of the array. Now, what is the complexity of that particular operation? Anyone?
Is it
Can you
a
repeat
full
again?
array?
One?
Is it a full array? I mean, do we have to move all the items?
No. I think it's empty. It's just empty.
Okay, then it's order 1.
Order 1. Now, if let's say that size of the array is 100.
So Rahul, somebody had asked to repeat the question as well. So
Okay. So the
yeah.
question is that you are given an array, right? It's an empty array, and you are asked to put a number in the very first location of the array. Right?
Oh, okay, got it. Thank you.
So what is the complexity? Right? It's order 1. Somebody said it's order 1. And the reason is, let's say if the size of the array is 1 or the size of the array is 1,000,000, it is still going to be the same. It's only going to take so much time to put that number, right? Let's say if somebody asks you to put that number in the millionth location of that particular array, then what would the complexity be?
1.
Will it still be 1?
Yes.
Why would it be 1?
Because we already know the positions of all the items in an array. So
Yeah. So because the underlying system, what it does is it keeps you know how it works, right? Because it keeps the address of the very first location of the array, right? And then it adds the size into whatever location you want to, right, to go to. And that operation, it's always going to be constant, right? Whether it is 1 or 2 or 3 or million, that operation to add the size multiplied by the location that you want to access to the base address of the array is always going to be a constant. So that's why it's order 1, right? Now, let's say you have an array and you have, let's say, an array of 10 numbers and you want to find a number in that array. Let's say you want to find whether 6 exists in that array. So what would you do, and what would be the complexity of that?
It's probably order n.
The order, but what would you do to find number 6?
Nice. You got to go through all the elements unless the array is sorted.
Yeah, so you go through all the elements one by one and you compare, and then that's how you get, right? So if the size of the array is 100, then the possibility is that your number is at the 100th location, right? And so you are going to go through an entire array and find out. So that is an order n operation, right? So let's see.
So if the array is not sorted, then the time taken to sort the array will also be taken into consideration, right? While knowing the time complexity, while calculating the time complexity.
So there are different ways you can do it. The way right now we are discussing is a very simple way, which is basically you are going to go through in the array one by one, and you are going to compare the number with the number that you're searching for, right? And that is an order, n operation. The search operation is an order n operation. Okay. So this is another interesting graph that this person has created, which is given an array. We discussed about search, and we discussed about uh, the worst cases. So typically, when somebody asks you what is the complexity, they are typically looking for worst case. Worst case, what is the performance of it? Sometimes they will also ask you average case, like, okay, average case, what will be the complexity of the solution or algorithm, right? But mostly it is. So now let's look at sorted array, right? Well, what if it's a sorted array and you are asked to, let's say, uh, insert a particular number in that sorted array? Then what will you do?
Insert at a particular index, like
Yeah.
in the middle of the array.
No, the sorted array, because it's a sorted array, you have to figure out where to insert it, right?
Okay. So the way I'm understanding the question is, we have a sorted array and we want to insert a new element.
Yeah.
Then because the position is not the constraint, we are trying to deal with a simple case, right?
Yeah. Position
Okay.
is not the concern. What do you mean by that?
No, because the way I understood is like where we want to insert is it up to us, because I don't know whether we have to insert the
Yeah.
middle of
So
the array or
middle,
towards the end of the
somewhere,
array.
somewhere in the array, so that the array is already always remains sorted.
Okay.
So what would you do in that case? And what would be the complexity?
We'll have to. My understanding is we have to split the array, or
No.
So
We
Rahul, would it be log n? Because if it's sorted, the time it takes to find the correct position is log n.
Okay.
And then there is an insert after that,
Yeah, insert. Yeah.
which is constant. Is it log n overall, or do we?
Oh, so let's say you have 1, 2, 3, 4, 5. Let's say you have 11 positions in an array. Okay, your array size is 11, and you have numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. Right? Right? That is it. You
So
don't
in
have
this
10
case,
right now.
probably we got to do a binary search. We have to take the number and compare with the average. If it is less than that, then compare with the average of the smallest number and the average.
Let me give you
Oh,
the
sorry.
problem, okay, and then you can think about the solution. So let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, right? And then somebody asks you to insert 10, right? So now what would your algorithm be?
So in general, the search will take log n, and then
Yeah.
the insert is going to be of order of n. So
Yeah.
since O of n is larger than log n, I mean O of n is going to trump.
Yeah, exactly. So I think you got it right. So what will happen is basically you will first search for that number, right? Now that number, whether you search it by using binary search or by using your normal search, it's order n operation, right? It's odd log n if you do search. It's order n operation if you do a simple search through the array, right? But once you find the location, right, then what you have to do is you have to move the array, right? If the array has space, then you'll have to migrate some elements out to create space for this particular number, and then you will have to put that number there. So that number, in my case, was the last element 10, but it could also have been that the array that we had was 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I got a 1. So in that case, I have to move all the elements by 1, right? So that's why it is order n at the order n. Does it make sense? And then the very fact that log n is a smaller thing than the order n operation that we are doing, which is to move the elements, it doesn't really matter. Log n it loses its significance, to say, because there is something which is much bigger that is going to take more, which will be more consequential to your execution time. right? Any questions? Okay.
So,
I think
so you said it is order of n is what you said.
Yeah, it's order n.
Rahul?
Yeah.
Because if it is sorted array, then we would know the index where we want to insert the element, right?
With that would take log n to find that, because you can do a binary search, right? Like if you have 10 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you want to find 6, you can go to the center of it and say, okay, oh, this is 5. That means that I don't have to now search 1, 2, 3, 4, because you know that the numbers are going to be smaller than 5 to the left of it. I only have to take the other half, right? So each time you do that operation, it becomes your size, search space becomes half and half and half. So you're able to do that in log n.
Correct.
The other thing is with a sorted array, it doesn't necessarily have to be that a number is going to exactly match the index to. You still have to search either way.
Yeah.
And the numbers in the sorted array don't have to be the index itself. It can be a larger number or a smaller number.
Yes. That what I'm trying to do is make it simpler for you to visualize and then understand. But what you said is right. Okay, so we are very clear on sorted array and array, right? And what their complexities are. Let's take a look at linked list. Do people know what a linked list is? Everybody knows what a linked list is? Hello?
Yes.
Okay.
Yes.
Anybody doesn't know what a linked list is? Okay, good. So everybody knows what a linked list is. So linked lists, in order for us to insert into a linked list, what do you think is the complexity?
It's constant.
And why is it constant?
Because we have to only change the positions of a couple of pointers. If you want to insert an element, you just have to change the pointer of the previous element and the next one to accommodate the new element.
Okay, so it has you're right.
It's a couple of constant operations.
The reason is that typically an insert into a linked list is done at the head, right? So you know the head, and then you're right. There are a couple of operations that you do, and that creates inserts it into the linked list, right? So it's order one operation. If you want to remove an element, let's say if you have to insert an element at some position in a linked list, then what is the complexity?
Then it will be order of n.
Then it will be order of n, right? Correct? What if you have to do the same operation in an array? You want to replace a particular number at a given position.
It's constant because we know where the element is. We know the indexes.
So you know that based on that, you can simply go and modify. And so linked list, when you want to go and at a particular location, you want to do something, then it becomes an order n operation. Whereas in an array, then why do people use linked lists? Why not always use array? Array insert is also one, right?
Memory management is more flexible when it comes to the linked list.
Yeah, linked list memory management is, you don't know, if you know exactly, I want 10 bytes, that number of, the structure of the array is that you know you're going to have 10, then you have to use an array, right? Because then it makes sense. Whereas when you don't know the size of input, or when you're not sure what the size is, then you use a linked list. A lot of times I've seen people make this mistakes during interviews where they don't know, they use the wrong data structure, and then they bomb the interview. But you see what I mean? So where to use linked list, where to use arrays. Search in a linked list is order n, right? Because you have to still go through the entire list to find where the element is. Can you do a binary search in linked lists? You have a sorted linked list.
Not unless it is already sorted.
Yeah, but if you do a binary search on a linked list, how will that work?
You have to have the index to be able to do a proper binary search.
Yeah, but index, when you do an index, right? If you have an index, that
Yeah.
means it's then you have O1 access, right?
Yeah.
Then it makes sense, right? But if you have an order n access, then what is the? You see what I mean?
So what are you saying? How can we still manage to do a binary search on linked list? Is that the question?
Yeah. No, does it make sense to do binary search on a linked list?
Not unless you actually have those pointers in an array. At which point you have access to the individual indices through the array's indices.
Okay. So yeah. So basically, essentially, then you must as well just put it into an array, right?
Yeah.
You know what the size of this is,
Yeah.
right?
Yeah.
Okay, good.
I mean, the only place where that makes sense is if the data object is so big that you don't want to allocate all those memory ahead of time, but you still want a fast access on whenever you want to search for it. I don't know. I mean, I really cannot find too many instances where this would be a very useful constraint.
Yeah, I
Hi,
agree.
Rahul.
Yes, hello, Chris.
What is the use of doing a binary search on a linked list? Because again, we are going back to the like array of the pointers, and it's again we are doing the operation on the array itself, right?
Yeah.
In the end,
That's
we just
what.
get the value, and then we'll pick the value from the linked list.
Yeah, that's what the conversation is. That does it really make sense? Is it even a worthwhile idea to pursue, right?
Yeah,
It doesn't make sense,
it
and
doesn't.
yeah, it doesn't really. I haven't seen many use cases where you would. Everybody knows what a doubly linked list is. Is there
Yeah.
somebody who doesn't know what a doubly linked list is? Okay, but it's the same thing. It's linked list with two pointers, which is one pointing to the front and one pointing to the back, to the next and previous. Okay. Stacks. So stacks. Can somebody give a kind of a brief description of what a stack is? Hello.
Stack is a data structure where you can insert or remove only from one end, and you can only, what is it, first in, last out. Is
Yeah.
that right?
Last out. Yeah.
Yeah.
You can only. So what are the various APIs that a stack provides? Common APIs.
Push and pop.
Push, pop. Yeah. Push, pop, and peek. Some
Peek.
peek. Yeah. Push is basically push the element into the stack. Pop is pop the element, and peek is just to look at what the top of the stack is. Right. So inserting into a stack, what do you guys think? So stack is an interesting data structure. What would you use to implement a stack? That would be an interesting question.
Is the question where stacks are used, or
No. How would you implement a stack?
Using an array.
Pardon, what did you say?
Using an array.
You can use an array to implement a stack. Could you
can
use a linked list to
list.
implement a stack?
Yeah, you can use a linked list.
Okay. So when will you use a linked list based stack, and when will you use an array based stack?
I guess if there is a need to look at any items which is not the top, not at the top, but you need constant access, maybe then an array-based stack
That
makes.
would be useful. Yeah.
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 If you don't need to know the elements
Yeah.
between, but you just need to perform the operations of a stack, then probably.
Also, you have to look at what domain you're looking at. Like, for example, if you know that, there are going to be 100 elements, they're not going to be more than 100 or 200 elements, right? You could use an array-based stack. But if you don't know how many elements are going to be there, right, then you have to go towards a linked list-based stack. Otherwise, what will happen is that you will have to increase the stack size every time the number of elements increases, right? And that would be an order n hit. So one of the important thing in stacks is this insert operation and remove operations are order one operations. That is a guarantee that a stack provides, right? So if you, let's say, overflow, right? If you insert, like with a linked list, you're always at the head of the linked list, right? So you are easy, it's easy. O1, O1, O1 is very easy, right? Correct? But in an array, if there's an overflow, like you need more data, more size, more arrays, more array size, bigger size, then what you'll have to do is you'll have to create a bigger array, right? Copy all the elements, and then discard of the previous array, right? And now when that hit will be taken, it will give you an order n insert. Does it make sense? Hello?
Yes.
Yeah.
And then, but that is still an order one operation because what they consider it as, it's called amortization, right? That you did n inserts, and at the end of the time, n, you had to give a penalty of n. So so you did one operation which was very large, but at the end of the day, if you look at, you average it out over all the inserts that you did, then it is still an order one, amortized order one complexity. Do you understand the concept of amortized complexity?
No, could you repeat that?
So you insert 1, 1, 1, 1, 1, right? Every operation is an order one operation, correct?
Right.
Now you insert the last element, it's still order one. Now you insert last plus one, now you have to take the hit, right? What you do is you will copy all the n elements into a different array, and then you will say, okay, this is my new array, and now I'm going to insert. So the complexity in this case, for the last one to hit, that last one that you added is order n, right? It takes n elements. But people consider the amortized complexity is still order one because the penalty is, if you distribute that penalty across all the n operations, right, then it's still that there's a little penalty that each operation had to pay.
Right.
Right. So that's called amortized complexity. And there are cases where you might have to kind of use that. Okay. Okay, hash tables. Everybody knows what hash table is? Or somebody doesn't know what a hash table is? Okay. So,
I would like to clarify.
Okay. What should I? Can somebody explain what a hash table is? Hello? No?
Hash table is a list of key value combinations of two elements, right?
Yeah. It's a list of key value elements. The very common interesting question that people ask in interviews is, how would you implement a hash table? Right? So how would you implement a hash table? So typical answer is that you essentially take some sort of a modulus function, hash function of the key, right? And what you could do is you could have an array of a fixed size, and with that fixed sized array, you would do a modulo such that one of the index of that particular array, one of the index of that particular array is chosen, and then that's where you would insert that particular element.
So,
Right?
how do you actually determine the size of this array or the bucket? Like, who decides the size of the bucket? How big it is? What's the size?
That's a very domain specific question. It all depends on how many keys are you going to expect, right? Typically what you want to do is you want to choose a hash function which is going to give you unique values, a unique index for each of the values that you're going to expect.
Okay.
Right? And then based on the number of expected values, you will choose a certain size. You're expecting 100 or 200. Typically, good idea is to do a 0.75 factor. 0.75 as your hash. If you're expecting, let's say, 100, then you allocate 75. That's
So, is it in the user's control or is it?
Yeah, it is in the user's control. Hash tables will allow you to kind of choose that factor. And then, so there are multiple approaches to implementing a hash table, right? One of the common things in a hash table is called collision. So let's say you are not very smart, and then you chose a hash table with an array which has an implementation of an array, and that size was like 5, maybe just as one array, right? And then what will happen is all your hash functions will go and index to that one location, 0th location. Now, then you have to store that number. And what people do is they create a linked list below that location so that you can add elements to it. Let me show you an example. Okay. Are you able to see my screen?
Yeah.
Okay, so we're going to do create a hash table of 10 cells, right? Now, let's say I want to insert, and now this hash function is the number divided by 10. Okay, so I have 10, and I can go to the 0th location, right? And now if I insert, let's say 20, it will again go to the 0th location. So see how it went. So this is called linked chaining. Okay. Now if I do 21, it will go to the next one. And right, so insert, let's say 31 will go to the second, right? Let me insert another like 41. You see what happened, right? So it goes to that, finds that location where it is indexed, and then it goes and goes down, and then finally inserts it. Let's say if somebody wants to insert 21 again, then what will happen? Already it goes, finds it, and then now let's say you want to search in this, right? Now in a hash table, one of the things that they say is that the hash table has a O1 search, right? So you're able to look up a key and get the value out of it, right? So in case of 10, it'll go and search. It will say, oh yes, it goes and finds the index 0, and then it goes and searches, right? You do 41, and then it has a little longer to go. It goes search, and then it goes down the linked list, right? So in chaining, what happens is that you have the order 1 is the operation to find the bucket where your chain is, and then you have to just basically traverse down the chain to find the value, right? So if, let's say, if you don't have enough memory, or you don't have enough locations, array location to store your to index, then you might as well have a linked list, right? in order to search for that value, you might have to actually go and do an order n search after your hash bucket has been found. So it becomes very important for us to choose a value, a hash function that will be unique and there is as little collision as possible. Does that make sense? Any questions?
Are there any hash functions? I mean, they try to minimize the number of collisions, but are there really? Would we be asked to design a hash function where there are?
Nobody, I don't think, except I don't know if Google might probably have some crazy person. If you find him, then he might ask you. But otherwise, I don't think normal interviews, I haven't seen anybody ask you to design a hash function. But they expect you to understand what are the different ways you can implement hash functions. Now, let me show you another way. Okay. So this is called linear probing. Okay. In this, it's still the same. The concept is still the same, right? Let's first do a 10, create a 10. Okay. And then in this case, you add a 20, you got it, right? Now, if you add 10, instead of doing a linked list, it's just going to store it at the next available location. You see what happened? So it goes, it signs, and then the very next it goes through the array and finds the next location, right? So this is called open addressing. So different ways of doing the same thing, actually. So this linked chaining is one approach. This is another approach. But the idea is that hopefully every number is you try to do it such a way that everything falls in its own unique bucket, and you don't have to basically do searching like this. Right? So search is order 1, insert is order 1, delete is also order 1 because you can go and look at that location and remove that element from there.
Insert is order 1 is because it's just finding the next open bucket, right?
It's not when you have to start to find next open bucket, then it is no longer an order 1 operation. The main thing is that the hash function that you have, that needs to be such that it generates unique values for most of your problems, for most of your keys, and that will guarantee order 1.
Right.
If your hash function is only going to return 0 or 1, then all your elements are going to be in 0 and 1 location only in kind of chaining, right? And then you have to go through that entire. Okay, binary search tree. Everybody knows.
I had a question.
Yeah.
So as you said that due to the collision, linked list is created, right? In the same this thing.
Yeah.
In the bucket. So can we since we know that there are only these many elements, what happens if we choose a larger bucket? I mean, if we have to compromise on the space due to not to have a collision, then how bad is it? Like, how bad is compromising on space?
It all depends on your problem, what you're trying to solve. Let's say if you're trying to build something in a very small memory constrained CPU, then you have to be very careful, right? In modern times, with gigabits of memories available, right? It's not that big of a problem.
Okay, so basically it depends on the situations.
Yeah, it depends on the situation. There are certain things also, like I read one paper which was very interesting. Twitter actually, I won't mention it right now. It was too advanced. I'll send that paper if I find it to the group on when they decided to use one strategy versus another. Okay. Let's go through binary search. Let me see if we have time here. So binary search tree, what is binary search tree? Anybody can explain it?
Basically, it's a binary tree where for each element in the tree, you have a left and right. And the left value is lesser than the root and the right value is greater.
Yeah, that's exactly. So binary search tree allows you to basically, you have numbers, you can, at each point, you can basically divide your search space in half, right? I should have, we actually went too fast. I didn't expect that we would reach here. Let's do binary search tree in next session, because I wanted to show some diagrams and things like that. We have 6 minutes here. I wanted to show this growth chart. It's very impressive, right? This is your chart that we saw last time, comparison graph, right? Order 1, on n log n, order n, n log n, O n square. And you look at this growth chart, right? You have, if you have 10 elements, log n is 0.003 nanoseconds, n is 0.01 second nanosecond, n log n is 0.03 n log. But if you look at like 2n, 1 nanosecond, right? And well, under 10 millis is still bearable. As soon as it becomes 20, right? N factorial becomes 77 years, right? And the number of input becomes 30, n factorial becomes like 8.4 into 10 raised to the power 15 years, right? Whereas the other ones are still manageable. But you look at around 100 or even 1,000, not even 100. Typically, our algorithms are like around 10,000, 100,000, even n square becomes very prohibitively expensive, right? It becomes 10 seconds. A million, it becomes 16.7 minutes, right? So kind of gives you an idea what range you can use what algorithms depending on the problem and how much time can the user wait, right? Sometimes it is much simpler and easier to implement an n square algorithm rather than trying to make it a log n algorithm, and that makes sense for that particular situation. Does it make sense? If you know that your numbers are going to be less than 1,000 and you know this operation is going to just take 1 millisecond to execute, then why would you want to spend time trying to write an algorithm which is log n complex, but it's hard to maintain? Does it make sense?
Yep.
Yeah. Okay, guys. I think for today we'll just stop at this. Any questions? Any other things that I can improve in this sessions?
You did good, Rahul. Thank you. Thanks for explaining very clearly.
Okay. Thank you very much.
So are we meeting Sunday for the same session? Is that repeat of the session?
No,
Or is
no,
that,
no. What I'll do is I'll
different?
publish out what we have done until today, right?
Okay.
And then we'll continue from where we left off. The course curriculum is exactly in that data structures class, that section that I created, right? What are we going to cover?
Okay.
Right? Those are the things that we are going to cover, and then it will repeat. And we'll modify and change it depending on what people think, and how we want to proceed, right? But I was thinking, so after this, I'll publish out where we left off, and then everybody can go and look at, okay, the next lecture, what are the things that we'll go cover. Well, so was it useful? Because I know a lot of people might have already known this stuff, because this is very basic stuff, right? How many people actually felt that this was really, really useful to them?
I felt it is useful.
Yeah,
So
me
Rahul,
too.
if you remember me, I worked in real networks.
Yeah, Krishna, I remember you very
So
well.
I'm an Oracle DBA. I did Oracle development, then I did ETL analytics. I did a little bit of Java, but I'm trying to do the data science. So I'm more interested in learning the algorithms and this programming. Otherwise, I did not do much of programming and much of concepts. So this is very useful for me.
And then somebody else that said it was useful. What is your background and why did you find it useful?
Yeah, this is Shruti. For me, it's returning back to the basics.
Okay,
I'm returning to the concepts after 2-3 years, so
I see.
it's good to start again. Yeah.
Good, good, good. Oh, okay, cool. All right, guys. Please feel free to email me or give me feedback. Okay, that way I can improve. And also, I want to know, like this basic class. When I took that survey, I just found like 4 or 5 people who were actually going to be useful. So give me feedback if to kind of say that, hey, does this really help you guys? And on a scale of 1 to 10, if you can tell me, how much does it help you? Great.
So, Rahul, quick question.
Yeah.
In general, are you open to changing the Sunday class timings, or is that something that's decided? The morning 9:30 to 10:30.
I think we'll be open depending on feedback from whatever you guys tell us.
Okay.
Okay.
Because I have a weekly commitment to 10:30 every Sunday, so that's why it's a little tricky.
Yeah.
I don't know how the team
Yeah,
or
you
everybody else.
propose a new time and then we will figure out
Okay.
if that
Yeah.
works for everyone or not.
Yeah. Otherwise, I'll just have to make alternate arrangements.
Yeah.
Okay. Thank you.
And I will post this video recording as well. So people will have.
Hey Rahul.
Yeah.
I mean, do you also plan to do take up a question and then
Yes.
solve it? Or
So there are going to be 3 series starting. I just wanted this one to see how it works and how people interact, right? Today I felt very comfortable. It wasn't like this Zoom.us just doesn't work for us. It works very well, even with 30-40 people inside the group inside. So what we are planning to do is lead code simple for people who are not there for medium, So they will hold a lead code easy, right? So you will go and solve lead code easy problems there, right? So people who already know all of this stuff, algorithms and data structures, the content that I have put down, they can start coding lead code easy, right? And then there's going to be one for medium and one for hard, right? So depending on where you find yourself, right? Because I don't want people to waste their time. If they already know all that stuff, there's no point in doing it again and again. It's better you find yourself with a group which is at your level. And then people can actually join 2, like one easy, one medium, because sometimes you're good at some other questions, but you're not at some certain concepts, right? So people who are medium might be saying, okay, I'll join the medium as well as the hard.
Okay. Yeah. This plan sounds good. Yeah.
All right, guys. Thank you very much. Have a nice week ahead.
Thank you so much.
Thanks, Rahul.
Thank you.
Thank you, Rahul.
Bye.